Then welcome back to EFT. Today we begin with a topic on expansion of loop integrals. Here I copied once again the so-called master formula of one-loop integrals, which we discussed in the last weeks. And here you have an integral which depends on one physical quantity q, and we integrate in d dimensions over the loop momentum k with some normalization factors, and we have calculated the result. The result contains a few irrational quantities which also depend on d, but in particular it contains q, the physical quantity, to some power, and the power can be obtained just by dimensional analysis. And from the loop integration we get a gamma function with a specific argument which also depends on basically the same number as the exponent here. And this gamma function can be either divergent, like 1 over epsilon, or it can be finite. And this formula is the basis of the definition of all loop integrals in dimensional regularization. And now coming back to effective field theory, what we need to understand which depends on one physical quantity q, and we integrate in d dimensions over the loop momentum k with some normalization factors, and we have calculated the result. The result contains a few irrational quantities which also depend on d, but in particular it contains q, the physical quantity, to some power, and the power can be obtained just by dimensional analysis. And from the loop integration we get a gamma function with a specific argument which also depends on basically the same number as the exponent here. And this gamma function can be either divergent, like 1 over epsilon, or it can be finite. And this formula is the basis of the definition of all loop integrals in dimensional regularization. And now coming back to effective field theory, what we need to understand is what happens if we have Feynman diagrams with different energy scales at the same time. So Feynman diagrams which depend on small momenta and large masses, or vice versa. And we want to do an expansion of such Feynman diagrams, because in effective theory it's supposed to be a systematic expansion in small ratios of either momentum divided by mass or something similar. So that means that we also should be able to do such an expansion of loop integrals which might depend on two different energy scales. And that is obviously non-trivial, and in the exercise that we will discuss on Wednesday, there is an example of a loop integral which depends on three scales, 2 light and 1 heavy, and you should discover that this loop integrals gives rise to partially analytic behaviors and partially non-analytic behaviors in the limit where the light scales go to 0. So it's a rather complicated dependence on such light small mass ratios. And today and in the next lectures we want to discuss the theory of such mass ratios if they appear in loop integrals, and this is done by an expansion of loop integrals. So, and let us immediately begin with a simple example. So this will basically give us a mindset, what we should expect and what we would hope for, and then we can discuss how it really works. So let us use an example, a fundamental theory that we have already discussed, similar to a theory which contains Z bosons and D plus E minus, so one heavy particle and a light particle, and the only interesting interaction vertex is the one where the heavy particle interacts with two light particles. So that is the only vertex that we consider now. And on the other hand, we have an effective field theory. And in this effective field theory, we use that the heavy particle is very heavy, and we do an approximation where we retain only the light E plus E minus degrees of freedom and integrate out the heavy Z boson. And in this way, at tree level, we know what happens. Namely, does anybody remember what happens at tree level? So at tree level, we do a matching of the EFT to the fundamental theory. The EFT must contain some Feynman rules which only depend on the light particles, but which reproduce Feynman diagrams with a heavy particle in the full theory. And here in this particular case, there is only one single Feynman diagram of interest at tree level, namely this one. This is the only Feynman diagram with a heavy particle and external light particles. And this becomes in the EFT an effective vertex. Let's today use a thick blob for the effective theory vertex, and that is just the outcome of the tree level matching of the EFT to the fundamental theory. And we know that this vertex would be of the order 1 over m square, where m is the heavy mass. Okay, so we know that, but now let us look at a one-loop diagram in the full theory. So, and the one-loop diagram is the one also from the exercise, namely two external light particles and a loop, basically with one heavy Z boson and an electron. So this would be an electron self-energy in this interpretation with a Z boson exchange. And this Feynman diagram exists in the fundamental theory, and we would like to describe it also in the effective theory. And the question is, how could that be possible? And so now let us guess a little bit and put in as much as we know from the past and try to imagine what could happen in full. So because we already know from tree level that the effective theory contains this vertex. So if the effective theory contains this vertex, then we already know for sure one Feynman diagram which corresponds to the light self-energy, namely which Feynman diagram definitely must exist in the EFT with two light external particles. Yeah. Yes, so like this, okay. So there is no way around this. This Feynman diagram definitely must exist in the EFT because the vertex exists. And if the effective theory is supposed to be a normal quantum field theory, then it must be that every vertex which exists can be used in the calculation of such a green function. So this diagram definitely exists. And now in the simplest case, maybe this Feynman diagram already fully reproduces that one. Could that be possible? That the result in the limit where the heavy mass goes to infinity becomes equal between those two diagrams. So you could see this from your exercise, for example. And we will soon also look at it in a little bit more detail, and the answer is no. So there is no way, and it is easy to see that these diagrams are the same, they are different. Therefore, even though this diagram definitely exists, it is not enough. There must be additional diagrams in the EFT in order to match to the fundamental one-loop diagram in the full theory. And which additional Feynman diagram could there be in the effective field theory? So there is no other one-loop diagram. So therefore, there must be an additional tree-level Feynman diagram with yet another new vertex, which we now introduce, which we haven't introduced before, and that must be such a tree-level vertex. This is the only tree-level diagram which can contribute to such a green function, and this vertex doesn't exist yet. It must be introduced now in order to match the two diagrams. So let's write this down. This must exist from tree-level matching. And here this might be required where this thing here is a new vertex from one loop matching. Maybe we can put a label one loop. So that means that this is a new vertex whose value is of one loop order because it arises from one loop matching. So, and this structure is the only structure which is conceivable. If the effective field theory paradigm should work at all, then it must look like this. It could be that the second diagram is 0, but it will not be 0. But for sure there cannot be anything else. So if DFT should work, this is the only option. Okay, so let us write down some expectations and observations. So first of all, on the analytic behavior. So this is your exercise. You have calculated this B0 function in the limit where the external momentum becomes small and where the mass ratio becomes very small as well. And so this is this B0 function of P, M, capital M. And who has done it already? So the others, please do it until Wednesday. So this is a very interesting and not too difficult calculation. So you have probably seen a difference in the behavior between P and M. Namely, the behavior in P is actually analytic if P goes to 0 or not. So it behaves like a... okay. So it depends like a power series on P. You can do a Taylor expansion and the Taylor expansion converges to the full result. So is analytic in P for small p. So that means you have a continuous limit, continuous derivative and so on. But it is not analytic in M. Non-analytic in M means that there exists no Taylor expansion at M going to 0. The derivative or some derivative diverges, because there is logarithm of M in the result. Okay, so that is interesting. And so please do that calculation. But even without calculation, you can now analyze, just by looking at the diagram, what is the analytic behavior of this diagram. So this is an A0 function, A0 of M. And the A0 function is directly given by the master formula. So Q would be M squared. So you would have M squared raised to some fractional power. Therefore, this result is also non-analytic in M, because it corresponds to M squared raised to a non-integer power. So it's non-analytic. That is actually not so bad, because it seems that it matches. Here we have something non-analytic in the small mass. Here we also have something non-analytic in the small mass. And maybe this gives us hope that the two non-analytic behaviors actually match, which we want, right? So that sounds actually good. And you already see here a simplification, because this diagram is of course much easier to calculate. And if the results were the same, then you would already see here a simple way to calculate the complicated non-analytic behavior of the full diagram. Okay. What about this final diagram here? And by the way, what is the dependence on the momentum p of this diagram just by looking at it. So at least in the simplest case where this vertex is just coming from the lowest order matching, then the vertex is a number, 1 over m squared times a number times a constant. Then this loop does not depend on the external momentum at all. Therefore it is a constant with respect to the momentum p. It's independent of p. But this diagram is not independent of p, and that is the simple reason how you can see that the two diagrams cannot be the same. Okay, but this diagram, if it exists, what does it have to be? It is a vertex in a local quantum field theory. Vertices in a local quantum field theory are always polynomials in the momentum. So that must be a polynomial. In P, because every Feynman rule must be a polynomial in the momentum. But here there is a question. In the theory of renormalization that we discussed the last time, we have seen that divergences also are polynomials in the momentum. So this is reminiscent of divergences. But we also saw that divergences are typically also polynomial in the masses of Feynman diagrams. Therefore, if we see this, maybe we can ask the question, if it's a polynomial in the momentum, could it maybe also be a polynomial in the mass? So that is a question. Also in M. So let's keep this in mind as a question. We would not be able to know it immediately. Okay, but this is the obvious behavior with respect to the small masses and the small momentum. Let's write down a few more properties that we can easily read off. For example, divergences. What about the divergences? So here this fundamental diagram has a divergence. You, I think, know it by heart by now. So these B0 functions have a very simple 1 over epsilon divergence, namely 1 over epsilon times 1. The coefficient is 1. So this is just proportional to 1 over epsilon. How about this diagram here? So in the lowest order, so where the vertex here is just 1 over m square, the vertex is a constant times 1 over m square, and this is an A0 function, A0 of small m. What is the divergence of such an A0 of small m? No. But it's dimensionful, so the A0 function has dimension mass square, so the divergence is m square times 1 over epsilon. Therefore you get here 1 over epsilon times small m square divided by big M square. So the small m square comes from the A0 function, and the 1 over capital M square comes from the vertex, which is 1 over capital M square. And that is the second reason how you see that the diagrams cannot match up, because the divergences are different. It's obviously different. So this has a divergence which is not mass suppressed, but this has a divergence which is mass suppressed. Therefore it's not the same. And the conclusion is that we need this diagram, and it needs to be divergent. It must contain the remaining divergence. So it is a divergent vertex. That means in terms of our renormalization, we could split it into a counter term plus renormalized coupling possible. So, but in the language of renormalization theory, this would be a bare vertex of the bare Lagrangian of the theory, which contains the sum of the counter term plus the renormalized quantity. So, and for this reason we also know that this Feynman rule must exist if the whole thing should work. Finally, let us look at something very important, which will be really the most important aspect of the discussion, namely logarithms. In the effective theory, we want to have a tool which gives us information on the low energy behavior of the fundamental theory, and this is often contained in logarithms of the mass ratio. Therefore, we want to understand logarithms. And so, first of all, we know here that there is a logarithm of mu square. What do we know about the logarithm of the unphysical mu square in this Feynman diagram? We know something very simple and very important. I hope several of you remember this. You remember it? Yes, very good. The coefficient is the same because it arises from this combination here, mu to the 4 minus d, and here 1 over epsilon. So whenever you have 1 over epsilon here, it automatically gets multiplied with mu to the 4 epsilon, and you can expand and get 1 over epsilon plus logarithm mu square. So always in one loop diagrams, yes, very good. The coefficient is the same because it arises from this combination here, mu to the 4 minus d, and here 1 over epsilon. So whenever you have 1 over epsilon here, it automatically gets multiplied with mu to the 4 epsilon, and you can expand and get 1 over epsilon plus logarithm mu square. So always in one loop diagrams, 1 over epsilon and ln mu square has the same coefficient. But mu square is unphysical. If you have mu square in the log, there must be also a physical dimensionful quantity also in the logarithm. So in this case, we have 3 dimensionful variables, p, m, and capital M. So there could be some combination of p, m, and capital M in the denominator, such that overall you get, of course, a dimensionless argument of the logarithm. Okay, but without calculation, we do not know which of the 3 appears in the log, or which exact combination appears in the log. And that is something which we would like to know, because then we would infer the logarithm of the ratio small m divided by capital M. That is what we actually would like to know. And without calculation here, we have no way of knowing. Now let us look at the logarithms here. What do we know about logarithms here in this result? Here, of course, the same argument is also true. So here we automatically get capital M square divided by big M square of logarithm of mu square, right? Because that is the same coefficient as 1 over epsilon. And we know something else, namely we know what is the argument in the log. If you look at the diagram, which of the 3 quantities can appear in the logarithm? How can the capital M enter? Right. Therefore, it's only the small m which can enter. And now we have learned something. Here we have an additional information, namely this is the only log which is possible. And here you already see how effective field theories give you additional information, because they separate the appearance of heavy and light energy scales in the problem. Okay, so here we have something specific. However, here we do not know anything without additional information. So here we need, of course, the remaining block. And the question is, do we know anything about this? So these are the questions. Now if that is the discussion of our example to shape our intuition. So we see that if we have such a loop integral in a fundamental theory with heavy and light energy scales at the same time, we hope that we can express it in terms of Feynman diagrams of an EFT, where only light particles appear in the loops. There is not a one-to-one correspondence between loops, but such a loop can be written as a combination of loop diagrams with light particles and tree-level diagrams or lower order diagrams. And there are some interesting relationships between the analytic behavior and the divergences and the logarithms. So 2 questions appeared along the way. So let's summarize them. The question was whether we know about this tree-level diagram that it must be a polynomial in P and the small masses. Let's keep this question in mind and check later. And also whether we know anything about the logarithms and the divergences of this tree-level diagram here. These are the questions that we should hopefully answer later. Okay, so do you have any questions to the example? And if not, then we can go on and do now the theory of the expansions of such loop integrals. And let me immediately give you the general method. There is a so-called method of regions. Which is a very general tool we can use to describe here such expansions. And let me immediately write down the statement. Which is from Benecke and Smirnov. From 98. And there is a very nice book by Smirnov as well. And a few review articles where he explains it as well. Okay, so the statement is as follows. Take a Feynman integral with several momenta and masses which are either large or small. Then we define so-called regions of our loop momenta. And each region is defined in such a way that each loop momentum is either large or small in the sense of these large and small parameters. So the statement applies also to multi-loop integrals. That is why I say loop momenta. If you have 2 loop, 3 loop diagrams, then of course you have different loop momenta. Each of them could be either large or small, and so you have combinatorically many possibilities. Then take each region, and in each such region of the loop momenta, Taylor expand the integrand. So before doing the integral, you take the integrand and Taylor expand it accordingly. So all the quantities which are small are Taylor expanded, and the large quantities are taken as large. Then you get Taylor expanded integrands in each region, so your integral is decomposed into a sum of integrals for each region, and in each region you have a different integrand because you Taylor expand in different ways. And after doing it, you do the integral. Integrate expanded integrands. But the trick is we use dimensional regularization over the entire momentum region. Momentum. So you do not restrict the loop momenta in the integral to be large or small or whatever, but nevertheless, after doing the Taylor expansion, you ignore that you were in some region and you simply integrate over the entire d-dimensional space. And in this way, sometimes there appear scale-less integrals. Scale-less integrals are integrals which do not depend on any dimensionful mass scales, and they are always set to 0. So that they are set to 0 is not a new property from this region, method of regions. It is a general property of dimensional regularization which we are using here, but I just write it here because it's very important in this method. We see it from the master formula. A scaleless integral means that q is 0. If q is 0, obviously the result vanishes. That is simply the statement. Okay, so this is the method of regions in short. And let me just say it is proven exactly for the limit that we use here, namely if you have small momenta and small masses compared to some big mass, if that ratio goes to 0, then this entire method of regions is exactly proven. But it is written in a very general way, so it would also be applicable to other kinds of limits where you do not have heavy masses but maybe something else. And then it is also useful and often applied, but not always exactly proven. So let's say also tested in many other cases. All right. So this is the basis of the next lectures where we will discuss this method of regions, apply it, and of course we will now do the example by using this method of regions and see what it tells us about this loop integral, because this method of regions will exactly reproduce obviously this structure here. So the method of regions for the example, and to simplify our life, we set the momentum now to 0 because we already know from the exercise that the momentum dependence is analytic, so it's less interesting than the non-analytic dependence for the mass. M is more interesting. Okay, so the integral that we want to look at is the B0 function, I over 16 pi square B0 with momentum 0, a small mass and a big mass, and the integral is defined as the integral over k of 1 over k square minus small m square times 1 over k square minus capital M square. And the integral is in d dimensions with the usual integration measure. Now we apply to this our method of regions and see what happens. So apply the rules of the method of regions. How many regions do we now have? The method of regions tells us that we should define regions of the loop momenta where the loop momenta are either large or small. And so how many possibilities are there here in this case? We have one big mass and one small mass and one loop momentum. So therefore the loop momentum can be either large or small. And therefore there are two regions, right? So two regions, loop momentum is either large or small. Two regions. And let us call the first region the soft region, where the loop momentum is small or soft. And the other one would be the hard region, where the loop momentum is hard or large. So in this region, we assume the loop momentum is of the order of the small mass. And in the other region, we assume the loop momentum is of the order of the heavy mass. These are the two regions. And that's all we should do according to this method. Okay. So then the method tells us in each region, Taylor expand the integrand accordingly. So in this region, we should look at the integrand and we should say k is of the order of m, k is small, m is small, k is small, and capital M is big. And we should do a Taylor expansion in the small quantities. So we should do a Taylor expansion where all of these three quantities are taken as small and only m is taken as large. So m is the only large quantity in the integrand. So we should do a Taylor expansion. Taylor expansion I will always write with a curly t operator, t. And here in this case we should Taylor expand according to k, m is much smaller than capital M. And so now for simplicity, let us immediately see that for this particular case, that is equivalent to saying that we do a Taylor expansion in 1 over capital M square. That is simpler. But it is equivalent, because that means we regard capital M as very, very large and do a Taylor expansion in 1 over capital M, which is then a very small quantity. And that is equivalent, since there are only the three quantities, to do a Taylor expansion in 1 over m, then to do a Taylor expansion in k and small m. It is the same. But it is simpler. In particular, it is simpler because Taylor expanding in 1 over capital M square, we can pull this out of the integral or inside the integral, it doesn't matter, because this only knows about the capital M and it knows nothing about the loop momentum. So it's actually quite nice to express the Taylor expansion in such a way which gets rid of the dependence of the loop momentum. Okay, so, but anyway, this is what we should apply onto the integrand. We do that later, but this is what we need to do. Let's first see what we should do in the other region. So here we say k is big. So k square minus small m square, that will now be Taylor expanded. K is a large quantity, m is a very small quantity, and we do a Taylor expansion of this. This will become a geometric series in small m square. And here k square and m square are of the same order. Here nothing will happen. Okay. By the way, in the previous case, so where k was small, nothing happens here. This just stays whatever it is. But here k is infinitesimal compared to capital M square, so we get a geometric series here from this term. Okay, and in the other case we get a geometric series from here, and that is unchanged. So we do a Taylor expansion in m is much smaller than k and capital M, and that is then simply equivalent to doing a Taylor expansion just of small m square and ignoring everything else. That will provide here, this becomes a geometric series and the other thing is unchanged. So these are the rules, and so let us now see what we get from this. We get two integrals. We get two integrals, a soft integral and a hard integral corresponding to the two regions, and for each integral the integrand has changed because of these Taylor expansions. So let's look at the soft integral first. I soft is the soft integral. it is the integral over k with the Taylor expansion with respect to 1 over capital M square of the whole thing, 1 over k square minus small m square times 1 over k square minus capital M square. And okay, maybe let's do it immediately. What is the result of this? Taylor expanding it. So maybe some good practice for you. What happens if we do a Taylor expansion, keeping capital M small and k, capital M is big, k is small. So the first fraction is unchanged, and the other one becomes a geometric series, sum over n from 0 to infinity of what exactly? So we get minus 1 over capital M square times k square divided by m square to the power n. Right? This is the result. So that would be our integrand for the soft integral. And so we can pull out the sum out of the integral. Then we have infinitely many integrals, and in each integral we have a definite integrand which contains this k square minus m square times something where k square appears only in the numerator instead of in the denominator. So big difference. Okay. Then let's look at the hard integral. So here we have Taylor expansion with respect to small m square of the same. Let's immediately evaluate it. So here we have now k is big, m is small. So something happens here, namely this becomes a geometric series, and basically the same structure emerges. N goes from 0 to infinity, and then we have m square to the power n divided by k square to the power n plus 1 in this case. Right. And then times the second factor where the Taylor expansion doesn't do anything, 1 over k square minus capital M square. So in this integral we have a structure where there is one denominator, k square minus capital M square, and here k square appears in the denominator but without a mass attached to it. So the integrals are quite different. Here we have an integral, thinking of normal Feynman diagrams, this would be like an integral with many propagators, but many propagators, n plus 1 propagators, are massless. K square to the power n plus 1 corresponds to n plus 1 massless propagators times one massive propagator. Here we have one propagator only with a small mass, but we have k square in the numerator. This can normally only come from vertices. So we would have a vertex in the Feynman diagram, which is of course a polynomial in the momenta. And here it's a polynomial in the momentum of very high degree, but only one propagator. So very different kinds of integrals. But of course, all these integrals are quite simple to calculate, and we will calculate all of them. But the method of regen tells us that the sum of the two integrals now is apparently equal to the original B0 function. Okay, so that is the claim. I over 16 pi square B0 is equal to I soft plus I hard, where n goes to infinity, of course. So, I mean, if we really calculate all the terms up to infinity, then it would be equal. And if we truncate the geometric series, then of course we have an approximation. And this is the systematic approximation corresponding to the effective field theory. So one additional thing is interesting about the integrals I soft and I hard, they are only single scale integrals. So the first one depends only on the small mass. Of course, you see here the capital mass, but this is really not part of the integral. You can trivially pull it out of the integral as a prefactor, but the integral, which is non-trivial and will be non-analytic in small m square, this depends only on small m square. And here the integral only depends on capital M square. And the small m square can be pulled out on as a polynomial. So you see that this is a polynomial in 1 over capital M, but not analytic in small m, and here it's vice versa. Polynomial in small m and non-analytic in capital M. So very nice separation of all the difficulties and all the dependencies. All right. How are we doing with time? We have 40 more minutes. Let us go on by actually calculating the integrals, because I think that is now more instructive. Maybe let's do it over there. Let us evaluate all the integrals exactly. Let us evaluate the B0 integral exactly, and then let us evaluate the soft and the hard integrals also exactly, and check directly that the results are the same. Okay? You can already start while I clean the blackboard with computing the B0 function at the top. Calculate the B0 function. What is the mathematical trick that we can use here to immediately calculate the integral, to reduce it to A0 functions? Maybe you applied it in the practical. Yes, partial fractioning, exactly. So we simply try to write it like this as a difference. So writing it as a difference, then bringing it to one common denominator, you see that you obtain a numerator, k square cancels, but you get small m square minus capital M square. Therefore, if you divide by 1 over small m square minus capital M square, this is the same. So you can check it by going backwards. And that is an extreme simplification. By the way, this is very often possible if you have numerators which contain the same momentum but different masses, like here, then this is a very typical trick. All right, so then we are done, because this is an A0 function, and this is also an A0 function with the 2 different masses, and therefore our final result is given by I over 16 pi square times from here A0 with the argument small m divided by m square minus capital M square minus A0 with the argument capital M divided by m square minus capital M square. Very simple result. So we have also managed, by doing the exact calculation, to separate the result into 2 contributions, namely one contribution which essentially depends on the small mass only, and one contribution which essentially depends on the heavy mass up to a trivial factor. So we have achieved this here as well. So of course this is not always so simple, and if we would have an external momentum, we couldn't do it like this. But here in this particular case, we can do it. And you see, also thinking always of the analytic dependence. So here this is non-analytic in small m. This is non-analytic in capital M. But this is essentially analytic in small m, in capital M square, or you could derive easily this into a geometric series by saying small m square is smaller than capital M square. Then it becomes either a Taylor series or a Laurent series in 1 over capital M square. And here the opposite. So here this becomes a polynomial in small m square if you do a geometric series out of the denominator. So the non-analytic behavior is separated. Now let us calculate what is the prediction of the method of regions. So we should calculate the soft integral and the hard integral on the one hand. And so we will do it immediately here with all n. That is simple enough. In practice, maybe you would do an expansion and truncate here the series in n at n equals 0 or n equal 1 at some low orders, but we can do the exact calculation. So let's look at it. Method of regions, soft. So the soft integral is the integral over all of k square minus small m square sum over n minus 1 over capital M square times k to the 2n divided by capital M to the 2n. And so here we need to do a small calculation. So how can we simplify this? So suppose we have such an integral k to the 2n divided by k square minus small m square. This is what happens here. Okay? This is the essence of the integral. How can we simplify it? We can simplify it by writing k to the 2n as k square to the power n minus 1 times k square divided by k square minus m square. But then we have here a reduced exponent, and here we do k square minus m square plus m square as a trick. Then what happens with the term k square minus m square in the numerator? Do you already see what happens in such a case? It cancels the denominator, and after the denominator has cancelled, we have an integral which only has the integrand k square to some power. What is the result of this integral? It is 0 because it is scaleless. This is such a scaleless integral which vanishes in dimensional regularization. So this gives 0 because of scaleless integrals. Okay, and therefore what remains is m square. So this numerator gives the same result as that numerator times m square. So we have effectively replaced 1 k square by m square. And we can now repeat the process and ultimately replace all the k squareds by m square, and therefore after n steps we have that the integral is the same as m to the 2n divided by the same denominator. So then we have iterated the same procedure n times, and then we have converted every k square into an m square. And then we have an a0 function. So therefore, the soft integral is simply given by the following. Every k square here is effectively equal to m square. So then we have k square minus m square sum, and here we simply have minus m to the 2n divided by m to the 2n plus 1. Okay, and that is now a mass ratio which can be pulled out of the integral. and that is only an A0 function. Therefore, we have A0 of capital M times this sum of minus m to the 2n divided by m squared to the n plus 1. A0 of small m, sorry, yes, thanks, small m. Okay, and what is this summation here? What is the result of the summation? Yes, so it will be 1 over m squared minus capital M squared. And then you discover that the soft integral is equal to what? It is equal to one of the terms in the exact result, namely it is exactly equal to this term. I forgot here the I over 16 pi squared. So, but the soft integral after summing over all n is exactly equal to the first term here. Now, we are very optimistic to look at the hard integral as well. So the hard integral has the following: 1 over, so sum of m to the 2n divided by k square to the n plus 1. 1 over k square minus capital M square, and we need to do a similar calculational trick. Let's do the calculation here separately. What happens if you have 1 over k square to some power n, and then 1 over k square minus capital M square? Or maybe let's do n plus 1, why not? Okay. Do you have a suggestion for a procedure how we can simplify this in a way similar to here, where we replaced effectively k square by small m square using such a trick? Can we apply a similar trick here where the k square is in the denominator? We need a slightly different method maybe, but which method could we apply? A method that we have already applied today. That is not possible because now we are to integrate over all of k. So in this integral, k can be large or small. So that was also part of the method of regions, that we now forget about where the integrand comes from. We integrate over all k, and then it's not generally correct to do the geometric series expansion. But you have already mentioned that we often do partial fractioning. So let's also do partial fractioning here. So let's, for example, let's do k to the n, and then we treat 1 over k square separately times this one, and we write it as the difference 1 over k square minus 1 over k square minus capital M square. Okay, so this difference gives rise to the product 1 over k square times that times a numerator. Which numerator do we get? We get minus 1 over m square in front. So we get times minus 1 over m square. And this is an equality. Now, if we have this equality, we again have two terms. What is the integral over the first term? Everybody? So it's 0 again because it is a scale-less integral which doesn't depend on anything, so this gives 0. And that is the same structure as in the beginning, just one factor 1 over k square has been replaced by 1 over minus capital M square. Okay, so basically we get again an iteration. We apply the same strategy n plus 1 times, and then we obtain minus 1 over m square to the power n plus 1, and we get times 1 over k square minus capital M square. That's it. By the way, the minus cancels, sorry, because here we also have a minus, so we have plus 1 over capital M square. So after all these steps, basically it simply means that this k square in the denominator can be replaced by capital M square, and then our hard integral is the following, is the sum of n, and so this becomes m to the 2n divided by capital M square to the power n plus 1 times I over 16 pi square times a0 of capital M. And then we see it is exactly the same as here, but the argument is different and the minus sign is different as well, and therefore we reproduce exactly the second term here. So therefore we see directly I over 16 pi square times the b0 function is equal to I soft plus I hard. The method of regen works. So this is the outcome of the explicit calculation here. So you see that in this particular case, maybe the exact calculation is not so difficult, and maybe it's even simpler than the calculation of the soft and the hard integrals. But you can see that structurally it will always be like this, that such a soft integral is only a one-scale integral, which is always simple, even in the case where the starting integral would be more complicated. And therefore you typically get a simplification here. But anyway, the important point is it works, even though we see here this non-analytic dependence on the small mass, which is also the outcome of the exercise. And the non-analytic dependence on the mass is reproduced by which of the two integrals, the soft or the hard one? It is reproduced by the soft integral, yes. The soft integral contains the non-analytic dependence on the small mass. And in Feynman diagrams, this corresponds to this diagram that we had in the beginning. This effective field theory diagram contained also the A0 of m, small m function. So this corresponds to that diagram that we have imagined right from the beginning, and it reproduces the non-analytic dependence on m. So now we see how it fits. And you see that you get also some structure which is similar to our expectation, namely this can be represented by such a Feynman diagram. And the other one is a one-loop diagram which becomes a polynomial effectively in the small mass. And so if we write the second, we interpret the second, the hard integral, as simply a new vertex, then the new vertex would be given by this. It's a polynomial or power series in the small mass. And if we had a momentum, it would also be a polynomial in the small momentum. Exactly what we need here. So the correspondence would be basically this and that. So, yeah. I think let us now spend maybe the remaining lecture on at least a sketch of the proof, why it works. I mean, I showed you that it works for the example. Let me give you more mathematical proof without doing the integrals, but using manipulations of the integrals, where you see how you could generalize also to other examples and how you could construct essentially a full proof that the method always works. This will also explain to you why we actually need to use dimensional regularization and how this thing that scaleless integrals vanish and so on, how this enters the statement. So let us sketch the proof a little bit more. Let us sketch more mathematically why the method of region works in this particular case. So, and in order to apply ordinary mathematics, we need to convert the dimensional regularization integrals into ordinary integrals. And in order to do it, we apply Wick rotation. Wick rotation brings us from Minkowski space to Euclidean space. And then we have, let's keep some space here. The integrand then looks like k square plus small m square times k square plus capital M square, so the denominators become positive definite. And we have rotational invariance in d dimensions, and therefore we can also go to polar coordinates and simply have here a one-dimensional integral where k runs from 0 to infinity, and we have from polar coordinates a factorial k to the power d minus 1. And then we have an ordinary one-dimensional integral, which we can discuss using ordinary mathematical methods, using convergence analysis and so on. So this is now our integral, let's call it capital I, which we need to discuss. First of all, since we work in dimensional regularization, even though this is an ordinary integral, dimensional regularization contains the prescription that we should always go to a region of the variable d where such integrals converge. Once they have converged, we get a result which is a function of d, and then we do analytic continuation of that function to all values of d where the analytic continuation is defined. That is the definition, and therefore, in order to apply ordinary mathematics, we first need to choose d in a region where the integral converges. So use d such that the integral converges. So in this particular case, d would have to be smaller than 4, then it converges. So once we have a convergent integral of one variable k which runs from 0 to infinity, we split the integral into regions. And here we simply say we have some cutoff capital lambda, which is between the small and the light and the heavy scale. So the small mass should be much smaller than lambda, and the capital mass should be much bigger than lambda. And lambda is then a parameter where we basically cut the integral into two parts, small momenta and large momenta, which means smaller or larger than lambda. So then we can split our integral I into I1 plus I2, which is obviously defined as the integral from 0 to lambda of dk of this integral plus lambda to infinity dk of the same integrand. And then we have two well-defined ordinary mathematical integrals. One of them has a compact integration domain, the other one doesn't. But both are convergent if d is big enough, small enough. Now, one of the two has small momenta. K is small here, definitely much smaller than capital M. And the integrand contains this fraction over there, 1 over k square plus m square. And in the first integral, k is always much smaller than m square. And then using ordinary mathematics, we know that the integral can be Taylor expanded in this fraction k square over m square without changing the integral. So let's simply say using ordinary mathematics. I1 can be Taylor expanded. So 1 over k square plus capital M square can be Taylor expanded, again in the sense that we use this operator T 1 over capital M square of k square over k square plus M square. Then this does a Taylor expansion in small k versus capital M. Similarly, I2 can be Taylor expanded. One over k square plus small m square can now be replaced by the Taylor expansion of with respect to the small m square of the same expression. Okay. And it is guaranteed to be correct. We can do the Taylor expansion under the integral sign, or we can do the Taylor expansion after the integral. Taylor expansion and integration commutes and converges to the true result in both cases, and so we have a guaranteed mathematically correct expansion here. So as a formula, we can definitely write I1 plus I2 is equal to the following integrals, namely integral from 0 to lambda, dk of this Taylor operator 1 over capital M square of the integrand plus lambda to infinity dk of the other Taylor operator small m square of the same integrand. So that is definitely true. So does that already correspond to our claim of method of regions? Because it's actually quite similar. We have split our correct integral into two integrals, one with this Taylor expansion and one with the other Taylor expansion. So there is just a small difference to our actual claim, namely what is the small difference? Yep. Exactly, so that is the difference. So here this is still ordinary mathematics and it is correct, but our method of regions would tell us now ignore the lambda. And nevertheless, here you integrate up to infinity and here you integrate down to 0. Even though in those other regions this integrand manipulation is wrong. It's clearly wrong. It's a bad approximation, but nevertheless we ignore this and integrate up to infinity and to 0 in both cases. And that is the claim of the method of regions, and therefore now we should prove that this is true. And it relies on dimensional regularization, so on using d as a variable which we can analytically continue with. So therefore, let us now simply by hand add these other parts and see what they do. Add by hand the remaining integrals. So let's call it I1 prime plus I2 prime are simply defined as the rest lambda to infinity dk of t over 1 over m square of the same integrand plus 0 to lambda dk of t m square of the same integrand. Okay? And now please have a look at what strange integrals we have introduced here. Because what is the integrand of the first integral? Here in the first integral, we have replaced the heavy denominator by a Taylor expansion. In this first integral, therefore, we have terms which contain k square over m square to the power n, right? if we do a geometric series here, we get k square over capital M square to arbitrarily high powers. Therefore, in this integral, the numerator contains very high powers of k. And this is true as long as we integrate up to lambda. But if we integrate up to infinity, that doesn't look good at all. Okay, so it was good up to here, but now it looks very bad. But here dimensional regularization comes into play. So this is convergent in dimensional regularization if we do something to the dimension. For example, concretely, if we have k squared to the power n in the integrand, what value of d should we take such that the integral converges? D simply has to be small enough. So let's say d smaller than, overall we have k to the 2n divided by k squared. So d should be smaller than minus 2n plus 2 or so, something like this. Yeah. So if d is smaller than this, maybe even negative, then the integral converges. And afterwards we can analytically continue. Similarly here. So here in the integral we have 1 over k squared to the power n. And that is absolutely correct if k is big. But if k goes to 0, that blows up and looks very bad. So the integral will diverge at small k unless d is big enough. So this is convergent if d is bigger than 2n plus 2. But the point is that since we use d as a continuous variable and afterwards analytically continue, we can define both integrals for some region of d, which is a finite region. Then we analytically continue, and then we can evaluate both integrals for the same d. And afterwards we can add them up. But while we have a convergent integral, we can also do more in I1 prime and I2 prime. We can further expand. Because now, so we have now a convergent integral, d is sufficiently large or small or whatever, the integral converges and k is always large. If k is always large, then in this integral we still have this propagator denominator. K is now large, therefore we can also Taylor expand the other propagator denominator. And in this we can do the opposite. So here we still have that propagator. We can also Taylor expand it because k is now small. Lo and behold, it means that we can Taylor expand everything in both integrals, and then the integrands become equal. So so let's simply say, let me remove this. So it's clear that I1 prime plus I2 prime can be written as the integral lambda to infinity dk of two Taylor expansions. Namely, we can Taylor expand in small m square and we can Taylor expand in 1 over capital M square of the integrand. And in the other case, we can do the same. Because now the k values are accordingly. And then the integrands of both integrals are now identical. And they are not only identical, but they are scaleless integrals. Because in each case, every denominator here has been expanded into a geometric series, and we either get only k square in the numerator raised to some power, or 1 over k squared in the denominator raised to some power. But there are no denominators like k squared plus anything anymore. So same and scaleless. And therefore, this vanishes in dimensional regularization. So the two incorrect integrals simply add up to 0 in dimensional regularization. That is the point. Okay, so and this is the reason why if we start from the correct mathematical expression and add these two incorrect terms, they cancel out between each other and therefore add up to 0. And so we can freely add them, and therefore we can drop the integration boundaries here. That is the point. So just to write it as an equation. We get, therefore, the original integral is equal to I1 plus I2 plus I1 prime plus I2 prime. These two cancel because they amount to scaleless integrals and they are mathematically correct. And in the end, that simply means we have integral from 0 to infinity of dk of our Taylor expansion in 1 over capital M square of the integrand plus 0 to infinity dk of Taylor expansion in the small mass as claimed by the method of regions. So this is the explanation why in dimensional regularization it works.
طيب هنا يا جماعة يعني في الحقيقة يعني أنا مشكلتي أنا بقطع الفيديو يعني أذهب إلى شغلات أخرى وأجي راجع مفترض أعيد الفيديو لكن لا أستطيع إعادته وبالتالي أواصل على هكذا وأنسى كثير مما ابتدأت به الفيديو. لكن إذا طبقت نظريتي ستجدونها صحيحة في هذا الأمر. عسى ولعل الأمر يعني الكونفرجنت والتايلر اكسبانشن ربما تجدون فيها نوع من الخفايا التي تؤكد نظريتي. يعني مثلا في السوفت نعمل الكي نعمل على انه اصغر من ام كابيتال وبالتالي تكون الباور الاكسبانشن في 1 على كي سي ان وان تتعلق بالدي باعتبارها دي يساوي ناقص 2 ام زائد 2 على ما اظن او ناقص 2 هكذا اللي هو يسمى بالريجولاريزيشن ودايمنشن ريجولاريزيشن كما قال. وفي الحرط نجد أن المعادلة هي عبارة عن كي على ام كابيتال كل سي ان هذه يكون التايلر اكسبانشن فيها. المهم إذا حاولتم معرفة ما بدأنا به الفيديو هذا الفيديو السابق بخصوص نظرية طريقة ستجدونه ينطبق تماما على الآلية المستخدمة هنا. في الحقيقة أنا أحتاج إلى مراجعة الفيديو من البداية لأنه كما قلت انشغلت بأشياء أخرى ونسيت ماذا أقول في هذا. المهم حاول أن تراجعوا وحاول أن توصلوا يعني بين هذه المفاهيم وهذه. ستجدون هناك أمر جميل في استخدام الميثود اوف ريجون بحيث أن تنطبق فيه نظرية تعريف. فالأمر يتعلق بكي مرة نجعلها يعني صغيرة ومرة نجعلها كبيرة. كي طبعا تمثل مومنتوم، وإذا جعلناها كبيرة فإنها يعني تمثل في ال EFT بالفيرتكس، اللي هي خطوة فيها نقطة فيرتكس، يعني معادلة الفيرتكس. عندما نجعل K يساوي M كابيتال، بالتالي لا، لن تكون الفيرتكس، سيكون الأخرى الخط مستقيم معه دائرة. لا، في الحقيقة يعني سأراجع هذا الأمر الثاني مرة أخرى. أنا قد سأنشر هذا الفيديو على هذه الحالة ثم سأراجعه ثاني.
So we use the property that integrals are defined for arbitrary d, always by going with d to the convergent region, then analytically continue, and scaleless integrals vanish, and both properties together combine to make the method of regions work. So this is a nice result. So here we could stop. Do you have any questions? Yep. Well, we will not do it. I will give you a few more pieces of circumstantial evidence, I would say, for the method of regions. But the general proof is quite cumbersome. And the logic of the proof is similar to the proof of...
أيوة، نعم. في حالة أنه في حالة الهارد اللي هو تمثل في الفيرتكس، نمثل أن كي صغيرة، وأن التايلر سباج يكون في ال M كي على M بسبب الكي صغيرة، وهذا يمثل زومين اوت في نظرية يوسف على ما أظن، هكذا زومين اوت. نتعامل بأن الأمر كله عبارة عن كتلة واحدة، هذا الفضاء ثنائي الأبعاد الصغير، وبالتالي نتعامل على أنه هو كتلة واحدة تخرج منه جسيمات، وبالتالي تكون السيريس اكسبانشن تكون في كي على M كل تربيع، وهذه الكل سين، وهذه يجب أن تكون convergent أو متقارب في الانتجريشن. أما وتمثل بالفيرتكس. أما الثانية فتمثل عندما نعمل كي كبيرة، وبالتالي تكون السلسلة في 1 على كي أوسين، 1 على كي أوسين، وتمثل ب هذا الخطوة فيه دائرة فوق له، وكي كبيرة. لماذا؟ لأن هنا نتعامل نعمل زوم إن، أي أننا ندخل إلى التفاعل بداخل التفاعل، فنجد أن كي كبيرة، وهذا منطقي أن كي تكون أكبر من M، لكن ليست أكبر من M كابيتال لأن هي خارجة من M كابيتال، لكن أكبر من M سمول. وهنا تحصل الكسر للتناظر، يحصل هذه الأمور لأنه كي كبيرة جدا، وهذه ما يحصل في داخل البروتون أو الجسيمات داخل البروتون مثل كواركات. نجد الكواركات أن كتلتها صغيرة، M سمول صغير، لكن الكي مومنتوم لها كبيرة جدا جدا، وبالتالي هذا زوم إن يعتبر زوم إن. و و وتكون السيريز في 1/k تربيع، 1/k يقصد على k أس، وبالتالي يجب أن نعدل في الدايمنشن ريجولاريزيشن. يعني كما رأيتم أنه واحد من الدايمنشن هو عبارة عن 2n زائد 1 زائد 2، والثانية ناقص 2n ناقص 2. هذا التعديل الذي يحصل بسبب أن dimension regularization يكسر التناظر، لكن عندما تعمل هذا التعديل فإنك تستعيد التناظر مرة أخرى. لكن عندما تعمل السيريز في 1/k تربيع، عندما k تكون كبيرة فإنك تكسر التناظر هنا، لكن تستعيده في الأخرى اللي هو عندما تعمل الكيس صغيرة تستعيده بهنا، وبالتالي المجموع يكون يساوي 0. هذا ما طلعت به، لكن ممكن أن تخرج بأشياء أكثر إفادة وأكثر متعة.
Renormalization in general, where you look at the structure of divergences at higher orders using subdivergences and subtraction of subdivergences and so on. I've given you the theorem, and the proof that proves that theorem is quite similar to the general proof of this. Because similarly, if you have a multi-loop integral, you need to first do the expansion of the subdiagrams and look at the behavior with respect to large and small masses of subdiagrams, and then step by step go to the big diagram. And so the proof has a similar structure, and in both cases the proof is rather complicated. And it is given in the book by Smirnov, for example, and also in some original literature references. But here I will provide you with a few more pieces of circumstantial evidence at least. Other questions? So next time we will begin with drawing the connection between this result for the integral and our intuition that we developed at the very beginning with the two Feynman diagrams, the one-loop diagram and the three-level diagram in the EFT. This is now basically explained by the method of regions, and then I will give you many more details on how you can understand why the method of regions works, and some additional details, and then we will also discuss actual physics applications and examples. Okay, then let's meet on Wednesday for the exercise.
إذا الحلقة القادمة ستكون مهمة جدا، وسأحاول قدر الإمكان أفرغ نفسي تماما لها. الحلقة القادمة ستكون مهمة جدا لأننا سنربط الأمر مباشرة مع نظريتي، وسأحاول بقدر الإمكان أفرغ نفسي لها حتى أستطيع فهم الأمر جيدا، أو أستطيع أن أربط بين الحلقات أو بين الفجوات، أو أسد الفجوات التي نمت من عن طريق اليوم الحركة الكثيرة اليوم والابتعاد عن الفيديو أو ابتعاد عن الأفكار المتعلقة بالمحاضرة. السلام عليكم.